Hey everyone, thank you so much for having me here. Thanks to Secure Chain Con for letting me speak as part of this conference. Quickly to introduce myself, my name is Abhisek Datta. I'm the creator and maintainer of VET, a free and open source tool in software supply chain security space. I am also the founder of SafeDep, which is a company working in the same domain. I had been a security researcher during the early part of my career, but kind of moved more on the software engineering and tooling side of things. I'll set the agenda for this talk. So at a high level, this talk is divided into three parts. I'll start by setting or establishing the problem of inherited risks from open sources. If you are a consumer of open source software, which is everyone, including us, then what are the risks that you should be aware of, particularly the problem of malicious code from open sources? Then I'm going to talk about what we do as part of our open source projects in terms of establishing trust on open source code at scale. So what we are building at SafeDep in terms of identifying malicious code from open source packages, I'm going to talk about in technical details with the goal of sharing, the challenges, what worked for us, what did not work for us, and how can the community leverage this. Finally, I'm going to talk about some of our open source projects like VET, like how the community can leverage VET in order to protect against malicious packages, or how our research can be leveraged. What are the next things? What are the challenges to be aware of in this particular domain? Before that, I want to start with a question. Do you use open source code in your application? This is a trick question, really. Everyone does, including us. We also heavily depend on open source code. What if I tell you unvetted use of open source code can get you hacked? And maybe many of you are already aware of the various incidents that have happened in the recent past because of malicious or compromised open source code. Let's start with a very obvious example of how we consume open source packages, say npm install express. If you're from the Node.js world, you would immediately be familiar with this particular framework and the command, right? Here we are installing a very popular web application development framework package in the Node.js ecosystem called Express. This means you are going to add the code from the Express package and ship it as part of your application. So do you trust Express? I mean, if you ask me, I would say yes, I trust Express because it has all the signals associated with it for trusting. Like it is very well maintained. There are multiple maintainers. It is backed by a very large and matured community. There are regular releases and everything basically that would allow you to trust a project. But in reality, when you are installing an open source package, it's not just that particular package. It is actually bringing in a lot of other open source packages as part of its transitive dependencies. So when you're doing npm install express, it's way beyond just installing a single package that you trust. It's actually installing a lot of other code from the open sources in terms of dependencies for npm. Now, if you are a software development organization, you might be having a lot of secure coding practices, code review practices, and all of that in order to ensure quality and security of the final application that your team is delivering. Now, when it comes to first-party code, you would definitely review it. What about all this code which is coming from open sources? Did you code review them? Probably not. Neither do we do code review of every single open source package that we can use. What if any one of these packages are compromised or malicious in nature? You would most probably end up deploying malicious code in your production environment or end up shipping an application artifact to your downstream users or customers which has malicious code. That's a problem. So, from a software consumer's perspective, there are two key problems when it comes to inheriting code from open sources. It can be vulnerable, in which case it is actually bringing in vulnerabilities in your application. You would typically do software composition analysis to identify known vulnerabilities in third-party libraries or packages that you are using in your application to protect against vulnerable open source. But the other key problem, which we are seeing at a tremendous rate today, is the malicious code from open sources. Think about it. Malicious code is different from vulnerability. Vulnerability is a mistake, a bug in code because of which has a security impact. It does not have any intention to harm anyone, right? But on the other hand, malicious code is created with the intention of compromising downstream users of open source, which is why malicious open source is probably a larger problem when it comes to open source consumers. We would start with a real life example. So this is a real malicious package which we found a couple of days back. We reported it to NPM. We got this particular package removed from NPM, as well as reported it to OSV. So if you search in OSV, you would see that this package is reported as malicious, and we are referenced as the finder for this particular issue. So what is this? The name of the package is Express Cookie Parser, which was impersonating the very popular cookie parser library for the Express.js framework. The original cookie parser library has more than 3 million weekly downloads. So you can imagine how popular the package is. Now, this malicious package had the exact same README as the cookie parser library. In fact, it had the exact same API compatibility for the cookie parser as well. So imagine you're a developer, you're building on Express.js framework. Now you need the cookie parser middleware. You would probably search in npm.js or Google about Express cookie parser. So what are the odds of you finding this Express cookie parser library and using it, assuming that it is the original one? I don't think every time developers would manually verify downloads and all of that, right? If you would have used this particular malicious package, it would have worked exactly the same way as you would expect the cookie parser middleware to work, except that it had one particular malicious package or malicious code in form of this cookie loader.min.js. So this particular cookie loader.min.js was also loaded as part of loading the Express cookie parser middleware. Just that it would do a bunch of things before allowing you access, or before allowing you to use the standard APIs from the cookie parser package. So what it does, it first generates a IP address of an attacker. So this was one interesting issue or interesting technique that we found. In most of the malicious packages, we found hard-coded IP address or hard-coded domain names with which it would communicate, likely the attacker controlled command and control servers. But in this particular case, what we found was a domain generation algorithm. It would generate IP address based on some seed data and a hard-coded key. And from that IP address, this payload would download another JavaScript file called startup.js, execute it on the infected system, then remove this particular line, this require cookie loader.min from index.js, so that anyone who was compromised does not see any specific TTP of compromise or indicator of compromise, right? So pretty smart about that. So this is the high-level overview of this particular malicious package. But if you are interested in the full technical details of what does the malicious package do, what does the malicious code does, how does the domain generation algorithm looks like, please you can read that as part of our blog on this particular malicious package analysis. Okay, so we saw a real life malicious package. Now let's talk about what we do in SafeDep in order to detect such malicious package with technical details. So our stated goal at SafeDep is really to protect software development teams against malicious code from open sources. So in order to do this, what we do is really continuously monitor supported open source package ecosystems such as NPM, PyPy, and Ruby Gems, and few more are coming for newly published packages. And whenever we detect a newly published package, what we do is we perform analysis at our end. If we detect any malicious behavior, we sometimes do static analysis, sometimes do manual analysis of the detected behavior, although given the scale of or the number of packages that we scan every day and the suspicious things that we find, it's not possible for us to manually verify everything, but we do look at suspicious flags or suspicious signals for popular packages. So what we do is that we either manually verify them, then get it reported to appropriate package registries such as NPM or PyPy, try to get it removed from the package registries so that people are not impacted, and then also include it as part of the OSV database so that any other tool can also know about this malicious packages. So this is what we are doing as part of our malicious packet scanning infrastructure at SafeDep. We do have a community feed. If you go to this vetpkg.dev/mal, you will see a continuous feed of packages that we are analyzing. This is almost near real time compared to what we see. So every time a new package is published on NPM, a job is queued at our end. Once we complete the analysis, it will show up here. So if you're interested in malicious package research or in general, how does some of the malicious package signals, evidences, and behavior looks like, you can probably have a look. The thing to note is that these results are 100% auto-generated. They are not manually verified, so there are chances of false positives here. Now, let's talk in detail about how we do it, right? So we started working on this problem, I think, in December last year, during the time when LLMs were at the was a huge hype. So we also started with trying to leverage LLMs because LLMs were very good at code, understanding code as well as generating code, right? So I started with doing some experimentation by using an LLM. I remember it was, I think, Gemini, earlier versions of Gemini, to analyze known malicious code from some of the known malicious NPM packages. And I found that it was pretty good. It could identify most of the obviously malicious code blocks and as well as extract evidences from code blocks, which if you have to do without LLM would be a lot of work. You have to build your own parsers, you have to build your own syntax tree analyzers, and you have to build your own, snippet extractors. So I thought that maybe LLMs are the thing, right? Because it will help you identify malicious packages. But then when we built our first system based on only on LLMs, and once we deployed it, we figured that it's just not possible to scale for all the packages published on open source registries with just by throwing code at LLM. And real life usage gave us this real life experience of LLM hallucinations. If you send a small code block to an LLM, it does a very good job. But if you send a very large minified obfuscated code block, it starts to show problems, right? The first version that we built, which was entirely based on LLMs, did not scale. At some point, it was producing a lot of false positives. It was not easy to combine our knowledge and opinion on what is malicious, what is not malicious as part of this analysis, right? Then the second version that we built was kind of flipped it a bit. We kind of added some functions, LLMs and function callings using, I think, if I remember correctly, LangChain SDK. It's what so-called agentic AI now, but back then MCP servers were not there, so I'm not sure we used to call it agentic back then or not. But yeah, it was similar. You would have an LLM uh, perform reasoning and chalk out a plan of action and then call functions such as pulling a package from package registry, extracting it, enumerating the files inside it, analyzing them, and then finally making a decision. This was even worse than throwing code at LLMs, because when I evaluated this with a bunch of known malicious package, every time it was producing different type of results. The plan used to look different for the exact same package when I was running it multiple times. And it was very hard to debug. Like, it was hard to debug why the LLM generated a particular plan. Maybe there are ways I was not familiar with, but it turned out that this approach would also not work for the scale that we were looking for. Finally, we kind of resorted to doing the hard work of building a static code analysis engine. So that's what we did. We built a static code analysis engine using TreeSeater as the parser and a bunch of custom plugins that we built in order to analyze the syntax tree. The core code analysis framework is again open source and available for anyone to reuse. But we did use a bit of LLMs. I will talk more about it as in future slides. So the reason why we kind of chose the static code analysis route was, compared to using only LLMs for code analysis, the static code analysis was much more faster and much more deterministic. I mean, in fact, it is 100% deterministic, right? We were not using anything non-deterministic as part of the static code analysis approach. We also needed to capture real evidence in code. So which is why we kind of leaned towards using static analysis approach instead of taking a dynamic or runtime analysis approach. Like, many people ask me that, why are you doing this static analysis approach? It's hard. You have to do a lot of work. Why not just run open source packages and see if there is a malicious behavior? The reason why we decided against that is because we wanted to capture real evidence of malicious behavior in code and not just on runtime. Runtime has its own challenges with libraries. You just can't run a library. So that is a separate problem altogether. Also, with the static analysis approach, what we wanted is also have a set of human knowledge about malicious code analysis or malicious code patterns captured somehow, and then use that to classify a block of code inside an open source package as malicious or not, right? For that, we still actually used LLM, the final last bit of classification. And we also wanted to, continuously improve this system. So it was much easier to, build plugins and improve these plugins on top of static code analysis or, conventional static code analysis than dealing with LLM-based applications. Finally, it kind of looks like this for us. So what we do is that as I said, we still use a bit of LLM for final inferencing, but we do have a very large set of filters that take care of all the package analysis before using any kind of LLM analysis. Specifically, whenever we are analyzing any package, say, let's say an NPM package, we would first fetch the package from NPM package registry, enumerate through all the files inside the NPM archive, use Yara rules. We use the Yara Forge project, which has a bunch of rules for known malicious patterns. So we use the Yara rules, and we already have this package insights information, like how popular a particular package is, what are the stars, how many forks are there, how many stars are there, what is the project inside, open source project associated with the package. Then we also built something interesting. We built what we internally called a code capability analyzer. Because if you remember, I said my initial experiment of throwing some known malicious code block to an LLM yielded good result. I don't want to throw an entire source file to LLM, but I want to throw a small block of code to an LLM and have it reason that is it malicious and classify it to the type of malicious behavior that particular code is doing. In our experience, LLMs are very good at that. So with the code capability analyzer, we performed conventional static code analysis of function blocks and basic blocks of code in order to identify if it performs some operation which are potentially risky in nature. When I say risky, it means it is performing, say, a network operation or a file system write operation or a process execution operation, right? So what we do is that we built some custom analysis on top of tree-seater parsed syntax tree. And what it does, it identifies the imports and function calls in the program and matches it with the language specific runtime. Say, for example, if you're using Python and if you have to, write a file, you would most probably import the OS package and call, say, os.open or os.write or something like that, right? Our static code analyzer for code capabilities, it would identify based on such imports and function calls inside those imports that this block of code is potentially performing a file system write operation, or this block of code is potentially performing a network operation, right? So all of this static code analysis, the YARA rules, package insights, project insight, all of this is done to filter out only those block of code which has very high likelihood of being malicious. And we send only that block of code to LLMs to confirm that if they're malicious and also identify the malicious behavior as well as do some metadata extraction like this MITRE attack framework ID and all these things, right? Finally, based on all the signals, so why multiple signals? Because say in a particular npm package, you have a lot of source files, right? It's not just a single file. So we are analyzing every single source file or every single file inside an npm archive or a Python package archive with this filters. And whatever files matches these filters, we are also analyzing those blocks of code with LLMs. So this way, we are generating a bunch of signals that this is a signal for a potential malicious activity in this file inside this archive, right? Finally, we combine all these signals along with our past knowledge of what are some of the common malicious behavior we are seeing, what are the common false positives that we are seeing. We combine all of them in a prompt and use an LLM for the final inferencing. The last step is more about contextualization of the decision making. Because if you imagine, code is code, right? A behavior in a particular library can be malicious, and the same behavior in another library may not be malicious. Say, for example, if you see some code which connects to some random URL and performs some data transfer in a cryptographic library, you would be probably be worried. You may consider that to be a malicious. But if the same behavior exists in, say, a SaaS SDK or an HTTP client library, you would not consider it to be malicious, right? Because it's required for meeting the intended purpose of that particular library or package. So that we can classify a behavior as malicious within the context or within the stated purpose of the particular package, we use a LLM in the final step with this stated purpose as the context and the set of signals that we have gathered from prior static code analysis and LLM based analysis. So the last step is where we finally classify whether a given package is malicious or not. We also benchmark this detection system with Datadog's known malicious packages dataset, which has over 5,000 known malicious packages. I will not go into the details of this. If you're interested in this, you can read more about it in our blog. And by the way, we covered around 96.5% of that dataset. Okay, now we saw a lot of things that we do to detect malicious packages. Let's talk about how does the community benefit from it. Any data that we produce from the package analysis service, which is a cloud hosted service for us, is available through APIs. So if you're a researcher, you can reach out to us and can, I mean, the API is available. We just have to find the right documentation for you so that you can get started. It is also integrated with VET, our free and open source software supply chain security tool. And you can use VET to protect against malicious packages as part of your CI/CD itself. Another thing that we do is whenever we detect any malicious package that we can confirm with manual analysis or through some other complementary analysis, we immediately report it to the package registry as well as to OSV. Recently, we have been credited with reporting multiple malicious packages in the OpenSSF malicious packages project and the OSV project. Okay, enough talk. Let's look into the demo. Uh, the malicious packages data is integrated with our free and open source project called VET. You can go to github.com, SafeDep, VET, follow the instructions to get it installed. So I'll quickly show a demo as part of this thing. Let's do VET inspect. Yeah. So this is one of the malicious package which I read about. It's not like we detected it because it has been there for since 2022. We did not detect it, but retrospectively, when we analyzed it, we found it to be malicious. So you can just submit a package for analysis using VET like this. It will tell you whether it's malicious or not, and it will give you a URL for checking the details. So when you open the URL, you would get something like this, right? So here you can see all the details on why this is classified as malicious. You can also integrate VET as part of your CI/CD. For example, let's look at a real example only. In this particular pull request, we are intentionally adding a known malicious package. This particular one, again, which was detected and reported by us. If you see, if you have VET in as part of your CI using GitHub Actions, it would look something like this. It would see what all packages are being introduced as part of the CI. It will check what is malicious and block the same. Cool. That's about it. Thank you so much. Hope this talk was useful. If you are curious about malicious packages research, do get in touch with me. If you want to protect against malicious packages, do try out VET. It's free and open source. Thank you so much.